My name is Markku-Juhani Saarinen. I'm not from a big company with employees here. I'm from the crypto SIG. I'm a professor of practice in a little university, Tampere University in Finland. So stepping the thing. So a little sort of update on the post-quantum crypto standards. So this had already happened last year at this time of the year. We have the new standards come out. These are the final versions of the standards. You can go to NIST and ask for a CAVP or FIPS certification for ML-KEM, ML-DSA, and SLH-DSA at this point of time. And the plan is that these will replace your RSA and elliptic curve cryptography within, let's say, the next decade. And RSA is being depreciated. We don't even necessarily teach that anymore in the crypto classes, and same thing for elliptic curves. So that's what is happening. So these are set in stone, and these are will remain the primary PQC algorithms. These are the most widely used, and in RISC-V, we care about quantitative analysis, and that's why these are the focus, because these are the most used algorithms. So of course, there's more algorithms coming. There's Falcon. It's delayed by government shutdown, actually. They say that the standard is pretty much done. That's FIPS 206. And HQC-KEM was selected this spring at the end of the fourth round of the standardization process. So remember that there was a post-quantum standardization process. All of these algorithms were designed back in 2016 or so. They were entered into the competition in 2017. We evaluated them for about 7 years, and then standards were written, and now we are here. HQC is interesting. It's a kind of backup algorithm for ML-KEM. It's based on a different problem. The reason why you would use FNDSA for signatures is that perhaps you want shorter certificate chains. The signatures are shorter. It's only about 600 bytes compared to the 2 or 4 kilobytes for dilithium. So there's some other things. There might be additional signatures coming up, but anyway, the top ones are the ones that we care about mostly in the internet. Then there's also Frodo-KEM somehow exists in Europe. It's approved for common criteria there. There's some, it's not for the general purpose internet use. It's mostly for like government encrypting modems point to point, that sort of use case where it's used. So it's not highly relevant for ISA design. So Andes, for example, when they were talking about their secure boot, they had a thing called zero-stage bootloader in there, which is in ROM. So if you don't have a PQC scheme in that place and you are doing tapeouts right now, you are already kind of late. So OpenData, for example, had a version of SLH-DSA in the zero-stage boot for a couple of years now. So this is because from January 2027, for example, the military here in the US and some other government use cases, they require CNSA 2.0 or a waiver in order to just buy the product, the silicon. So given the timelines of the transition, one should be doing it already. So CNSA 2.0 no longer even has RSA. So your RSA is not used by the government. You know, you can just drop that, and actually the hardware, the sort of compute that you do for PQC is so different than elliptic curve or RSA that, for example, the big integer unit is quite redundant. So that's a big transition here we have in the crypto world. This is the European timeline for companies, for organizations mainly. So it will be sort of pushed forward in the NIS2 directive, and also by the Cyber Resilience Act. So there's some kind of a legal muscle behind moving this transition. It's pretty much the same algorithms as in America. The dates are similar. These three things, everything should be complete in 10 years by 2035. This date is shared with the UK, America, even Australia. I think all of the Western countries have these dates. There's a couple of interesting things to note here is that within 5 years we have the high-risk use cases, but also software and firmware update. So a hardware engineer reads software and firmware update as secure boot. So this is, zero-stage boot is in ROM. So you need to really update the hardware in order to support post-quantum boot up within 5 years in all products, including consumer products. So CRA, the Cyber Resilience Act, will cover that. So yeah, it's a pretty heavy requirement. I hope people are like wide awake about this. Yeah, everything before 2035. And the situation is actually this, like all good things, all good security should happen completely without people noticing. A police operation, let's say, or military operation is perfect when no one knows about it. And so currently about 50% of the internet traffic from human origin is already PQC encrypted. So it happened by stealth. One night Google just updated their Chrome browser and their entire cloud infrastructure to support this ML-KEM hybrid handshake, and your phone was contacting whatever Google Mail server using this hybrid scheme called X25519 ML-KEM 768. If you go and check your connection, for example, here's Amazon saying that, yeah, TLS 1.3, and then at the bottom we have this hybrid scheme and your PQC. So it's about half of the traffic in there. And you can imagine doing a handshake. Every TLS connection requires a handshake. So there's some additional latency involved with that. And because it's now doing both. It's doing the elliptic curve thing and the post-quantum thing for every connection. And that's why in ISA design we care about this. So we want to eliminate all such latency and the energy consumption of this fairly computationally intensive effort. So yeah, it's already consuming a lot of cycles in a data center that's serving a lot of pages. Every connection needs to be, every handshake needs this ML-KEM setup. So a little bit of background really quickly. We have a thing called Post-Quantum Cryptography Alliance, which is actually a sister organization of RISC-V International, because we are both under Linux Foundation. We are doing an open source software stack for post-quantum crypto. So there's a couple of projects here. I'm talking about ML-KEM native, which is the ML-KEM implementation. From this project, then there's other things like ML-DSA, SLH-DSA, which is the hash-based thing. I actually wrote that code. And some other, there's a Rust version, for example, out there and so forth. It's mostly C code and portable. So this is the governance structure. The maintainers are from Amazon and a little Taiwanese startup called Chelpis. And to describe basically what's going on inside this ML-KEM implementation, it's good to sort of give you a rough idea what it is computationally. So ML-KEM, what you need to do is mostly this sort of a ring arithmetic, which is on the right, and then you have a massive amount of SHA-3 operations or shake operations. We call it a Keccak permutation, which is the workhorse here. These are about 50-50 in a classical microcontroller implementation. If you have a nice vector unit, then that speeds up the right-hand side, the arithmetic part, quite a bit, and then the relative portion of the Keccak operations is even larger. It can be 70% of just computing that one 100-line loop unrolled. So that's a clear optimization target we have. And on the right hand side, so traditional crypto acceleration was big integer arithmetic. You would do modular multiplications of 1000-bit or 200-bit numbers in elliptic curves. Here we don't do that. So the big integer unit is not used. Yeah, so this is our strategy we had when implementing this library, is that we start from a reference implementation and then we add this sort of a researchy optimizations in there incrementally. You can always fall back into the reference implementation. And also we have formal checks. We have a really extensive like a testing infrastructure for this implementation because it's in production use. The liboqs, which is originally was like an experimental library, now uses this implementation currently as the standard one. I mentioned being from Amazon, so Amazon put this in production use. they have a lot of IoT targets, so the continuous integration is actually pretty crazy. You do an update, it's running on 300 different targets. It takes forever, but it's our implementation there running. And then it's also a provider for a Rust wrapper, which is widely used, Rust TLS. That's our code. So what we did is we have now RISC-V support, RISC-V vector support in this library. And that was merged actually 5 days ago. And this is like the announcement now of that. Yeah, so we have modularity. So the backend, for example, on how to do the Keccak permutation can be swapped out. And that's the FIPS 202, that's the Keccak standard. And various like assembler optimizations can be plugged in fairly easily because it's a portable library running on basically any target. I think they now even have a branch on AVR, like 8-bit up to high-end vector for the same library, from 8-bit upwards. So this is basically the main thing I'm here to talk about. We have the same targets, the same piece of silicon, a RISC-V vector processor. This is the X60, the common cheap Chinese chip that everyone uses for these things, in academia at least, because we don't have any other silicon. I have 3 bars for these operations. In terms of cycles, we have blue one, which is with intrinsics. So the implementation actually just doesn't use RISC-V assembly. It uses the vector intrinsics in order to speed things up. Then I have the red bar for auto-vectorization, especially LLVM. The late versions are really good at auto-vectorization. And then we have the no vector. It's still the same piece of silicon. It's just that the compiler was not told that you have vector instructions available. You get about overall double speed up by enabling our intrinsics. So that's nice. So more connections per second for your server and so forth, Amazon and other places. So the basic findings are that using intrinsics and auto-vectorization about 2.4 times faster or 2 times faster with GCC. Intrinsics relation to the auto-vectorization, you get about 30% or even 50% in GCC just by using our additional code. And a little bit about the comparison between the compilers. So if you have an older compiler and a newer compiler, you actually get you are 30% faster. So that's really important in a server environment when you're serving web pages quick and you want to shave off every cycle from the handshake, for example, then use a new compiler. So then it's funny that these compilers, there's roughly no difference if you don't use vectorization. All of the speed up comes from auto-vectorization, not the other optimizers in the compilers. So that was kind of the thing. So there's a different approach. So of course, Android devices, the Google software stack is this boring SSL, and it's all in pure C. I completely understand them. They want to have easily maintainable code, so it's just C. We have in ML-KEM native, we have a crazy amount of complication because we do formal proofs and everything, but they want maintainability. So we have formal verification, mostly about type safety and memory safety using a bounded model checker. We have so type safety is like what Rust does anyway, so it's fairly similar what you get out of there. It's in continuous integration. Assemblers implementations also do like an actual formal check that the assembly code matches with the mathematical model that's done with HOL Lite, but we don't have this kind of model for the RISC-V instruction set, so we don't do that yet. The timing attacks, which is fairly basic, it's written for that. That's a standard graph for a cryptographic developer. We know how to write constant time code. And then we also check for violations of our RISC-V constant time instruction set, which is in the spec, it's in the manual. We call it DREL, data independent execution latency. So these are the ZKT and ZVK V key T extensions. K is for crypto, T is for timing in these extension names. So we've had this for a couple of years now. Then we have a sister project, which is the ML-DSA, the signature scheme. That's also being done. That doesn't have RISC-V support yet, but the Intel target and the ARM target are fairly complete. So we have proofs for the front end and back end for these things that we prove, which is type security and memory safety, basically buffer overflows and such. And constant time checks and the testing infrastructure, which isn't quite as crazy as in ML-KEM native. I should say that having very, very extensive continuous integration can be actually kind of a slowing down factor for your development. So you probably want to enable that only after you're pretty sure that you are stable. All right, so that's the sister, the current backends for the ML-DSA. Now finally, the instruction proposal that we have for PQC. So I mentioned that most of the compute that we do is on Keccak. So we are proposing a single instruction that just does Keccak. It's one vector instruction. It eats up 1600 bits. That's 25 64-bit values from your register file. It doesn't fit into a single vector register. You need a register group and writes it back. That's what the instruction does. And if a vector implementation of Keccak is about 2,000 cycles or 2,000 instructions perhaps. With this, we can definitely have it in, I'd say, 40 cycles with all of the other latencies in there. It's a very significant speed up that we get from this instruction. So it's unusual. I've been a little shy in pushing this forward. I suppose I should again bring it to the architectural folks. Now that they are doing crazy things with the matrix extensions, they might actually, this might get a pass that, oh yeah, we are doing other silly things with the vector groups as well, so why not do this? So we have Spike, we have benchmarks, but no hardware POC. That's a tricky one because I need a high-end application processor in order to do a proof of concept of this. So scheduled by the end of this year. So last slide about future work. So we need to optimize a little bit further. We need a hardware POC for that. But anyway, it's in the main branch now, so it's in production. You know, the ML-KEM native code in PQCP. Okay, so yeah, happy to take questions. I hope I have some time.
Quick question, you mentioned the formal model of instructions that you could verify against.
Yeah.
Have you played with the formal backends for sale yet?
Yeah, so I mean, one would then have to translate. I know that sale code can be translated into multiple things, but we have not translated that into whole light. Yeah, that would be interesting. And anyway, last time I checked the vector support for sale, I think it's now there. Yeah, it might be a potential. For a long time, it was like not quite there yet. Yeah. The sale model wasn't complete. All right, thanks.
Thank you.